this talk is about writeahead logging, which is a technique used in database systems to guarantee atomicity and durability, which are two properties that databases must maintain. And in Postgres, it's also the mechanism underlying the implementation of replication. So it's quite central to Postgres. So let's pretend that we're a database server. Take a deep breath, focus your thoughts, close your eyes if that will help you get into the right frame of mind, and try to feel like that. But don't worry, it's only for a little while. Now, suppose somebody submits this transaction to the server. It's a simple update which sets a particular column in a table according to a where clause. In response to this, we need to try to make some changes and then tell the client what happened. Either the transaction fails and we have changed nothing, or the transaction succeeds and we have made all of the required changes persistent on disk and the data is safe. Of course, before we get to that point, there are a lot of things that need to happen. We need to parse the query, identify that T is the table that we're interested in, look up T in the system catalogs, prepare a query plan for execution, find out which files store the table's data on disk, open those files, scan the table either sequentially or using an index depending on the query plan, identify which rows match the where condition, modify those rows, and finally write those changes out to disk. Fortunately, for the purposes of this talk, we can skip over all of those steps. We're only interested in the last part, which is how the server writes changes out to disk in a way that maintains atomicity and durability. The operation we're interested in is fundamentally a very simple one. You have a file, you open it, seek to some position within that file, write some bytes out, and you're done. We may need to do this for several different positions and several different contents in the same file. We may need to do it for multiple files, depending on what we're trying to change. But this is the basic operation that we're looking at. And when it's described this way, it seems to suggest very straightforward implementation that you could use, which is just open the file, seek, write, close, and you're done. So the rest of the talk is basically about why databases don't actually do this. While trying to analyze the behavior of a database, two things that we should keep in mind always are correctness and performance. In terms of correctness in this area, we must guarantee atomicity to the users of the database, which means that a transaction must either fail and change nothing, or succeed and make whatever changes it desires to, and make them safely, so that they are durable, which is the next point, so that once a transaction succeeds, we don't lose that transaction data anymore. And of course, we must do both of these things while still maintaining a high level of performance. Another thing to keep in mind is that databases operate in a very hostile environment, and they must necessarily take a very pessimistic view of the world. The database must guarantee correctness even though the power may fail at any moment, even though the system might crash, whether due to a hardware failure or a kernel panic, even the database software itself may crash, and to some extent, the design of the system must take that into account and try to recover from it. Of course, disk can also crash and lose all of the data. There might be other catastrophic events that, as a database, we can't do anything about. But we have to try to recover from as many failure scenarios as possible so that we don't lose data. Now, write-ahead logging is, in a way, a technique to manage the risks of interacting with the persistent storage subsystem. So to understand write-ahead logging, we have to take a look at the storage layer and understand what those risks are. Yeah. Now, when we speak of a disk, we're referring to any one of dozens of different kinds of devices with very, very different physical and performance characteristics. Some of them may use magnetic platters or spinning rust. Some may use solid-state devices, optical media. There's a whole range of possibilities. Some of these devices have very simple controllers that will do little more than allow you to just read or write data. Some of them have very advanced controllers that use complex algorithms to optimize both for performance and for things like media lifetime. So there are now disks which will transparently remap sectors when they feel that the disk is prone to failure in a particular area. There are SSD drives which will perform wear leveling over their surface, as it were, by moving data around by themselves, not in response to any request from the computer. And some storage devices have battery-backed caches that are designed to survive power failures. Some have additional caches that are for performance, and so on. The reason we can talk about a disk without being completely overwhelmed by this diversity of devices is because of the marvelous abstraction that is the concept of a block device. So whether we're talking about 8-inch floppy disks or a rack-mounted network computer that exposes a few hundred disk drives as a single volume on the network, we can just hand-wave away the specific differences and focus on a common subset of functionality that they provide, which is based on the block device I/O model. So as far as we're concerned, this is what a block device looks like. It's a collection of fixed size blocks which contain some number of bytes, typically 512 bytes in modern devices, sometimes 4 kilobytes. The disk or storage device provides random access I/O to a minimum of 1 block at a time. It's not possible to ask a disk to read or write less than 1 block's worth of data in one boot. Of course, you can request more than 1 block at a time, but in terms of writing blocks, the disk guarantees only that writes to a single block are atomic. We'll look at what that means. And the other important characteristic is that storage devices are much, much slower than RAM typically. So each of these characteristics has profound consequences on the design of our database system. So we'll look at them in a bit more detail. Disks are slow, and this fact has led to a system design which has caches at many different levels. Disks themselves have caches. The drive controller may have a separate cache, which, as I mentioned, it might be for persistence or performance. which might be to protect from power failures or just a performance measure or both. Then there are different levels of caches in software. The kernel maintains a buffer cache. Applications like Postgres might do their own caching on top of that for various reasons. Any of these caches may be write-through, which means that if you put some data into the cache, it will be immediately sent to the next lower layer. Or they may be write back, which means you don't really know when the data is forwarded on. All you can do is submit it, and the cache will decide when the data should be written further. That's a problem because as an application, you want to know that something you have written has actually been stored on disk permanently in a way that you can rely on it being there at a later date. Unfortunately, that is not a guarantee that the application can make in any particular system. It depends on how the system is configured. The best we can do as a database is to use a function exposed by the kernel, which is used to flush the cache. So the purpose of this function, typically called fsync or whatever, is to make sure that whatever data you have written to the disk has actually reached the disk. Whether that is true or not depends on the actual configuration of the system. So if you're running a database server on some particular hardware, as a DBA, it is your responsibility to try and configure the system in such a way that flushing your caches actually results in the data getting written to disk, which unfortunately involves configuring the disk drives, configuring the disk controllers, configuring the kernel, and so on. So it's a very involved process. But what we also need to remember is that no matter what, flushing your cache is an expensive operation in software. It's a slow thing, and you can't just do it for every bit of data that you write. It will kill your performance completely. The next characteristic is that disks, as we saw, are block devices. They have no concept of byte-sized I/O. You cannot request a drive to read or write just a few bytes. If you want to modify 1 byte inside a block, somebody has to read in that entire block, modify that 1 byte, and write out the entire block again. So if you care about performance, you have to forget about byte-oriented I/O completely, which is the first reason that the simple code I showed in the beginning doesn't work for databases. It completely kills your performance. The next characteristic of block devices is the guarantee they provide that a write to a single block is atomic. If you write 1 block, it is either not written at all, and you can rely on that, or it is written completely, and you can rely on the fact that all 512 or 4 kilobytes of data have reached the disk. If, as an application, you are writing multiple blocks to disk, you have to be prepared to lose some of those writes. If you write 2 blocks to disk, the disk may write 0 blocks, or it may successfully write 2 blocks, but it also maybe may write only 1 block, and you can't even be sure which of the 2 blocks will be written. So you have to be, at an architectural level, prepared to recover from lost writes when you're changing multiple blocks on disk. There's a special case of this problem, which is called torn pages in the database world, which arises from a mismatch between the size of blocks that the database uses or the application uses and that the disk uses. So Postgres by default will use 8 kilobyte pages, as they're called. whereas most disk drives use 512 byte blocks. If Postgres writes out an 8 kilobyte page, which as far as Postgres is concerned, it's a single unit, the disk drive may nevertheless write only 1 or 2 or some number of blocks smaller than what Postgres actually submitted. So in theory, you cannot have torn pages if the database and the disk agree on the block size. So if you make Postgres use 4 kilobyte pages and you use a new disk drive that natively supports 4 kilobyte pages, which is quite a recent phenomenon, you can't have torn pages. But that doesn't mean that you can't have the problem, because if you have to modify more than one block in any case, you may lose some of those rights. So technically it's not a torn page, but it's the same problem really. Now, atomicity at this level is not the same as the A in ACID. This is a guarantee that the storage device is providing to the application that is writing to it, and not the guarantee that the database provides to its users. In other words, single block write atomicity is a building block that the database can use in order to provide whatever behavior it desires. So to summarize, the power may fail anytime, you may lose writes, but we still need atomicity and durability, and it has to all be very fast. And that means that, as I said before, we cannot just flush every write to disk after doing it. That kills your performance. Putting all of these characteristics together, a picture begins to emerge of how applications that care about high performance disk I/O need to model their I/O. Typically, you will keep in-memory copies of any disk blocks that you read as you read them. If you need to change anything, you make the change in memory in your copy of the disk block, and you mark that page as dirty, which means that it now differs from what is actually on disk, and at some point needs to be written out again. And you write out whole dirty pages at a time. So basically, if you have to modify the same block twice, you shouldn't write twice. You should do the changes in memory, and once you're sure you've done whatever you need to, at some point you can write out the entire page in one go. Now, this is primarily a performance-oriented organization of how to do I/O. It doesn't make any of our problems with lost writes or partial writes go away. It's just how you need to model your I/O if you want decent performance. And this is, in fact, how the kernel manages disk I/O. As we saw before, if you're using byte-oriented I/O, somebody has to translate it to block level I/O before it reaches the disk device, because that's the only block level I/O is the only thing it understands. And in nearly every case, that's actually the kernel's job to do that translation, which is expensive. As described here, the kernel maintains what is called a buffer cache, which is exactly a bunch of in-memory copies of any disk blocks that it has read in. And it does exactly that. It makes modifications to those blocks in memory, marks the pages dirty, and then has a separate process that looks for dirty pages and writes them onto disk when the kernel sees fit. The kernel may decide to delay or speed up a write depending on the conditions of the system and depending on some configuration parameters like dirty ratio, dirty background ratio, and so on, which in effect allow you to tell the kernel, don't bother writing out stuff until there is so much, or until it's become old, until it's y seconds or y 70 seconds old. And all of this happens at the VM layer, the virtual memory layer in the kernel. In a separate layer, where the kernel interacts with individual block devices, it uses its best judgment of the system's workload and of individual I/O requests to schedule whatever requests it's submitting to the block device. And typically, this is done by a component called the scheduler, and you can tune your scheduler or choose a different scheduler or whatever, but basically it's up to the kernel how it, in what order and in what, at what time it submits I/O requests to the actual device. Now, coming back to the database server, Postgres also maintains its own cache of 8 kilobyte pages, which is the default page size, in shared buffers. This is on top of the buffering that the kernel already does, but for various reasons, the kernel buffer cache doesn't provide enough control to Postgres for the things it needs to do. But the way the shared buffers in Postgres works is pretty much the same thing as the kernel. It's a copy of pages that are read in from disk. They are modified in memory, marked dirty when they're modified, and in this case, a process called the BG writer will go through shared buffers looking for dirty pages and writing them out to disk according to its best judgment. Now, we have some idea of how to manage block device I/O in a way that doesn't kill your performance. Now we have to solve the problems of missing writes and so on. Write-ahead logging is one of the techniques that databases use to do this, and it's not a Postgres-specific technique. It's a widely known and widely used method in the database world. But of course, it happens to be central to the Postgres implementation as well. Now, conceptually, there's a log file which is separate from the database. If you need to change anything in the database, first you describe what you want to do, what change you want to make, write it to the log file, flush the log to disk to make sure it's to make as sure as we can that it is being stored safely. Then we tell the client that the transaction is committed at this point before we make any of the changes. Tell the client that the transaction is committed, and then go ahead and change the data. So in effect, you say, I am going to make change XYZ for every single thing that you want to change in the database. You write that down, and then you proceed to make all the changes separately. And in particular, you don't need to flush the changes. And it's critically important that your log entries are flushed to disk before you actually make the changes to the data. And we'll see why that is. And also note that this log file is append only. You just keep writing descriptions of any changes you make. You just keep writing them to the end of the file. So the access to this file is purely sequential, and although flushing it to disk is always going to be expensive, it's not as expensive as if you had to flush a whole bunch of random writes to various parts of your disk. So it's the best case scenario for flushing things to disk if you're writing sequentially. So what do we get from this? Using write-ahead logging gives us a complete change description for every change that we're making to the database, and those descriptions are stored in a durable fashion. which means that if the database server crashes at some point, you can replay those changes, as we'll see, in order to bring the database back to a known good state. It's not obvious how this mechanism actually provides these guarantees that we need. So we look at a few possible failure scenarios. So the sequence is write to the log, flush the log, tell the client that everything is okay, and then actually go and make the changes. And when those changes to the data will be written out depends on the PG writer process, which is looking for dirty pages and flushing them to disk. So if we crash before writing the log entry at all, then we know that we didn't tell the client that the transaction committed, because we do that only after writing and flushing the log. So we know that we haven't made any promises to the client that we need to keep in terms of transaction management. We know that we didn't make any changes to the database itself, because we do that only after telling the client okay. So in this case, the database was in a known good state before. It happened to crash, but there's nothing we need to do in order to fix the database. We haven't made any promises, we haven't made any changes, we're all good. 2, if we crash while writing the log entry, we don't know exactly when in this process we crash. So the log entry may be partially written. We might get only a little piece of it, or we might get all of it or none of it. We just don't know. It depends on when the system crashed. So when the database is restarted after you reboot the system or whatever, and it enters what is called val replay, the thing that allows it to deal with this situation is that every log entry is written with a checksum at the end. So when you read in the log entry during replay, you check if the checksum is all right. If the checksum is all right, you know that the entire record was actually written to the log, because otherwise your checksum would fail. And if the record is okay, you can replay the record, which means that whatever change is described by that record, you just do that change again. You go to whichever block you wanted to change and change whatever bytes you wanted there. If the checksum is bad, you know that this record was not completely written, and therefore that you must have crashed while writing it. So you just ignore the record and stop. And your database is back in a known good state. Either you have done the change or you have not done the change. The third scenario is if you crash after writing the log entry. So again, we don't know exactly when this crash happened. We might have said okay to the client, yes, your transaction is committed, or we may not. We may have made some changes to the database, or we may not. But in either case, we know that we have a complete log record available, because the crash was after we flushed the log. So in this case, you just take the record and replay it. You don't care whether some of the changes were made, none of the changes, all of the changes were made. If you just make the changes all over again, then you know they're all made, and your database is in a known good state with all of the changes that were recorded. And any changes that were committed, if we happen to say okay to the client, have been recovered. So all is well. Now, something you might have noticed here is that we are not very concerned about writing out the changes to the database. We've been focusing entirely on making the writeahead log durable. And of course this makes sense, because if the writeahead log is durable, then you can always reconstruct any change that you intended to make to the database. But of course, writing out the data to the disk is also important. And in practice, you must limit the amount of log entries that you replay after a crash, because replaying all those changes takes time. And obviously, after a crash, you want your database to come back up as soon as possible. So write-ahead logging goes hand in hand with checkpoints. And checkpoint is an occasion when you know that all of the dirty buffers that you had in memory waiting to be written out have actually been written out and have been flushed, right? But the important thing is that it's not each write which is flushed. You have a whole bunch of writes which are queued up and waiting. You do them all, and then you flush once, right? So you amortize the cost of flushing your caches over a large number of writes, and you can configure how often checkpoints happen and so on, as we will see later. But once a checkpoint happens, you know that your database on disk is completely up to date with all of the changes that we have seen in the write-ahead log so far. Right? So if after a checkpoint something happens and the database crashes, you just started the checkpoint and only replay log entries from there on. You don't need all of the older log entries are now obsolete because we know that all the changes have been safely saved to disk. Right. Now we've been talking about the concept of write-ahead logging with a few details from Postgres sneaking in here and there, but let's look at how write-ahead logging works in Postgres. So in Postgres, the log file lives in the pgval subdirectory of your data directory. It used to be called pgxlog before Postgres 10, but I can barely remember those days now. It's not an infinite file that keeps growing, because what DBA would actually want that. So Postgres uses a series of 16 MB files which are called while segments. And as checkpoints are executed during the operation of the database, the older while segments are recycled, which means that instead of creating a new 16 megabyte file and filling it with zeros or whatever, you just take one of the old files you don't need anymore, rename it, and start using it again. And the log file records have something known as a LSN, or log sequence number, which you can think of as the address of the record in the stream of change descriptions. Right. Now, finally we get to the point where we can actually look at some while records instead of just talking about them. So we will just use as an example the transaction that I showed in the beginning, and we just want to see what kind of while records this will generate. And before I do this, I have to actually create a table and stuff, but that's boring, so I won't show it to you. We also don't care about all the while that was written before our transaction. So I'm sorry that it's eaten up some of the output. It's just making my part. But before we run the transaction, we execute the pg switch while command, which forces Postgres to use a new while segment just to isolate the changes that we're making. Yeah. So we do that, then I run the transaction, and then I switch while again. So now I have 3 while segments, one from before the first switch, one from during the transaction, and one from after the second switch. So the middle one, 2, is the one that we're interested in. And we turn to a tool called pg_while_dump, which is your best friend if you ever want to look at any kind of while records. It takes the name of a segment file as input, and it produces a human readable description of every record which is in that segment. And it produces summary statistics of all the record types and so on. So this is what happened when I ran pg_while_dump on the segment number 2, which contains changes from my transaction. and it has a few records which are not immediately relevant to the transaction, so we'll skip over them and look only at the records which were generated by the updates that we did. So you can see RMGR heap entries, which identifies the type of the record as belonging to the heap code, which is the code that deals with tables in Postgres. And you can see that it did 3 hot updates. And then at the end, there's a RMGR transaction, which is the transaction control subsystem in Postgres. And the transaction commits. I won't go into the details of what the record is actually saying, but at a high level, it's basically describing each of those single tuple updates which happen as a consequence of the this update command. Yeah? And at the end of making all those changes, the transaction commits, and we're all good. At the end, you can also see that there is a switch record that is displayed by PGval, which is what happens when you run PG switch val. It says ignore the rest of this log segment and switch to a new one. Yeah? And correspondingly, I mentioned checkpoints earlier. Checkpoints also need to be val logged because during replay, you need to be able to find the point in val that you know things are all right. So here, if you look at that redo value, that's actually telling you where in the stream you can start redoing from, because all older val is obsolete. All the changes are flushed. Here are some more val records from random deletes and inserts that I did on the same table. If anyone is very interested, please find me after lunch and I will be happy to walk you through this. I'll skip over this because I'm running out of time. And I'll just say that so far we've been looking at a copy of the database plus a copy of every change that's made to the database. And there are 2 questions and we use this for local crash recovery after the database dies. And there are 2 questions we can ask about this. What if the changes being replayed aren't local? And what if we don't crash before replaying them? So congratulations, we just invented replication. If we take a complete copy of the database, give it to another machine, and send a copy of all our val records to that machine, then it can make the same changes that the primary server does, and therefore have an up-to-date copy of the entire database, and process read-only queries as the hot standby implementation does in Postgres. So the only thing to do is that it has to get the val changes somehow, and there are a few ways of doing that, whether you send the whole segment across, or you use streaming replication, in which case the segments are irrelevant and you just get a complete stream. Those are just minor operational differences in how the replication works. The basic idea is the same. You're just sending all the changes you're making here, and that machine makes the same changes there. Finally, a word about logical replication. It is still based on the same writeahead log that is used for physical replication in Postgres, but there are no references to physical blocks anymore. The description of each change is done on the basis of the primary key of the row that is being changed, and rather than saying change x bytes at y position, the changes are described as columns and values. And the other big difference is that whereas physical replication is all or nothing, you must replay all of it or your database is broken. With logical replication, you can be selective about what you're actually replaying. You can only replicate changes to certain tables or certain databases, or even certain parts of tables and so on, simply because the descriptions are logical and not block level changes. So you have the freedom to search for your rows matching some condition and update them as the record describes. Right. I'm done. If anyone has questions, I'd be happy to try and answer them. Yes?
Abhijit, without the transaction,
Yeah?
if we do a switch,
Yes?
it doesn't switch more than once.
Okay, maybe. If there's nothing to do, then I'm not sure that's true actually. I'd have to try it out and see. We can do that after lunch. I would be surprised if that were the case. But maybe there's something which prevents it from writing a 0 byte clause.
I was trying to do some troubleshooting, but I wanted it to switch, check some.
Find me after lunch, we'll sort it out. Yeah? Anyone else?
Inside, you told about non-pages, right?
Yes?
So if page size of PG and data
And the list, yeah?
are equal, then how we can have non-pages?
You can't have torn pages if they use the same block size. But if you're changing multiple blocks, which as a database you have to do at some point or the other, then there's no guarantee, right? You may write the first 4 KB page and lose the second one.
Ultimately, we cannot do full page writes.
No, full page writes is a specific optimization for the case where the block sizes differ. Yeah, okay, sorry. That's a complicated answer. Find me afterwards and I'll show you how it works. Any other questions? No? Okay, finally, please stop pretending to be a database now. Thank you.